Alright, this is a short summary, called Summary Edition, on virtual memory management. So I'll be touching on a few of the critical things that any CS person should know, should be on your fingertips. Right? So let's go through. Now previously, this is the third video I've done concerning memory. If you have no idea about memory, please note that there are some topics that together form memory management. The virtual memory, some people consider it to be part of memory management. Usually when we say memory management, we talk about having processes, having these processes have different types of addresses, virtual and physical addresses. If you don't know what that is, I think it's good you find one of my previous videos or read the textbook Silver Charts. I think chapter 8 covers that one. There are different ways that memory can be partitioned, different ways that memory can be placed, as processes are placed in memory, that's this point. And finally, there are different schemes for mapping the virtual addresses to the physical addresses. Right. But in this one, we are trying to see what more is there about memory management. Right. And I think what is more is figuring out how we can share, or more processes can use much more virtual memory than they have physical memory. For example, and that's with the first point, you may have 1 gigabyte of RAM, but you may have a process that has 4 gigabytes of memory. How is this done? This is usually part of the virtual memory part, right, where we talk about what are all the algorithms that make this easier. We also will hope that you appreciate virtual memory. Let's just say physical memory. I keep making these mistakes. So virtual address space and virtual memory, right? So we're hoping that you appreciate that a bit more. And we'll go through some algorithms. So replacement algorithms. So if you hear things like least recently used, most recently used, you should have an idea what these algorithms are. We'll also be looking at the page table. You remember from the previous section, the page table was how the system was keeping track of which virtual memory pages are mapped to which physical frames. A frame, and I know the term is different, a frame is just the same thing as a page, but a frame means a page that's currently in, or a piece of physical memory. And we also talk about some issues with page replacement, in particular thrashing. Right? And I hope that everyone knows what thrashing is by the end of this. Right. So why do we need virtual memory management? So we talked about memory management, that is getting things into physical memory, but we also now are flipping it the other way. What about the virtual memory? What are the things that we do with the virtual memory? So I hope you are understanding the two parts. So when it comes to memory, we always said there was physical memory and virtual memory. We would say there's logical addresses and physical addresses. So it means there are two things we manage. In the previous lecture, we talked about the main memory management, and now we are flipping it over to virtual memory management. Maybe they should have called that physical memory management, but anyway, there's different ways, so you know why we're going through this. Now we need to know how to put processes in memory. Processes that may not fit in memory, make it work. Now the second part is there'll be multiple processes running in memory, so we have to figure out a good way to do this. And if we come up with good strategies, we should be able to offset any issues with I/O, and I/O meaning input-output. So the operating system and the hardware has to figure out a good strategy to move pages in and out of memory. Now, one way to think about processes is they are like customers who are ordering for items, saying, I want this book, I want that book, or maybe even saying, I want to have a type of car, I want to have this type of car. And if you are the service provider or the company, you would like to have a good strategy to bring to the customer things they will need. Now, I'll give you examples. So this is not main memory or virtual memory, but other examples that you may have seen. So for example, you go online and you start to type something in a search engine. The moment you start typing, your search engine sometimes will give suggestions. And even sometimes before you even start typing, it would bring up a few pages or some ads, meaning that the search engine or the system is anticipating some of the things you may need. Right? And this thing, it shows, in a way, it can guess and guess wrong, but if it guesses right or figures out what are the things you're likely to need and brings them to you before you even click, Somehow think that is improving I/O, improving your work. So these are the main things that virtual memory will be concerning. Right. Now, previously, so this example is from the previous discussion, but when we looked at it, we realized that in memory, some people saw what happened, but they didn't. But I'll point out that, for example, this process OS has 0, 1, 19, 20. Those are virtual memory pages. But that means that actually there are many pages that are currently not within main memory. So this is like my fake representation of main memory. So sometimes, and this actually says this process OS wants to use 20 pages, or 20 in this case, when the pages are here in physical memory's frames, wants to use 20 frames, and we can't give everything that the process needs in memory. So what we do is we play this game, as I said, where whenever you ask for something, we would map and say, oh, your 0 has currently been moved to, for example, virtual has been moved to physical 12, and maybe 20 has been moved to 1. So anytime you ask for something, we move it into a room for you. So it's almost like a company or an organization that has many employees, and these employees are sharing a workspace. And so that means anytime an employee walks in, they can go to any desk that is available, and their stuff is moved to the desk. So we don't expect all the employees to be there at the same time, but then when an employee shows up or needs to come in, we set up a space. So an employee shows up one day, we tell them, hey, today you are in page number 1. Maybe next time you will not be in, frame number 1. We could put you in frame number 15. So that's the idea, because there is limited resource and we're trying to share it for everybody. Right. So this is the simple paging that we talked about before. And this data structure over here is the page table. And for this specific chapter, we'll extend it a bit. Right. So the first extension we do, so that we know whether or not the entry we have in physical memory is valid or not, we have a valid bit. I'm writing these out with words, but in computing usually it will just be a binary or a bit, like 0, 1. I'm just writing valid and invalid, so you grab onto this quickly. So for example, this would say I have OS with 0, 1, 2, 3, 4, 3, well, there's 4, 5, and so on, 19 and 20. This is what my page table looks like, and it says that page 2 and 3 of virtual memory is invalid, meaning that it doesn't actually exist in physical memory, right? And that's possible because sometimes when a computer is running or a process is running, it hasn't used up all of the memory. I mean, it knows it all belongs to him, but of course, it, or him or her, I don't know what process it's okay. It knows the process, it knows all the memory that belongs to it, but if it hasn't used it yet, there's no need for that part of memory to necessarily be, that part of the virtual memory to be brought into physical memory. So we have the virtual memory and the physical memory. So when you need something, we bring it in and you use it. So that means that we need to keep a flag, that's a valid bit, to keep track of what things are in and what things are not in. So this is very simple. It's just like if you have, I think most of you are students, you have a student hostel. That means that there is a chart, and anytime a student moves in, they mark it as, oh, this room is in use. And when nobody is using it, they say, oh, this room is not in use. So valid, invalid is the same thing. It's just like saying it's in use or not in use. And when it's not in use, that means that you can give it, so for example, if I say virtual address 10, that's 2, is currently invalid, that means that it hasn't been brought into physical memory. When we bring it into physical memory, then we have to enter the address, the physical frame address, where we've actually placed what we brought from storage. So that's how we are dealing with this. We're going to extend on this a bit. So the extension is, when processes are running, there's also this thing called reference bit. The reference bit just means, did you make use of it? So for example, we could set up a room for a person, but maybe the person never used it. Right, so that means if the person never used it, we'll say no, it's never been referenced. But the moment the process has used it, we say, oh, it's been used. And this would help you figure out which pages, especially when we are running out of space, or we want to free up some physical memory. We will be moving the things, ideally, we will be removing the things that we know you have not referenced. Now, there's also what we call the modified bit. So modified means that maybe you've made a change to the page, right? Or you made a change to that part of memory. If you make a page to a part of memory, it means that before we kick it out of main memory, we have to store it back to this. We have to store it somewhere. So if a page has never been modified, we don't have to bother with saving it. It's just like a file. If you open a file and you didn't edit it, you can just close the window. But if you open a file and you've modified it, that means that closing isn't just a matter of I close the window. It also means in terms of modified, it has to be saved. So if I have a decision to make 2 pages where one has just been referenced and one has been modified, I know that if it's referenced, then it means that you may use it again because you referenced it. And if it's been modified, it means that if I'm going to kick it out or close it, I will have to save it. There's also what we call reference count. Reference count is an extension on the idea of referencing. So reference was 1 bit, 0, 1. Modified was 0, 1. But we can also count how many times have you used this part of memory. And that's also an important criteria, because it's just like if I have a bookstore. So that's another example. So many examples. If I have a bookstore and I have many books and people keep asking for a specific book, the more times people ask for the book, the higher has to be the reference count, so that I know that this book is very popular. So reference count is like popularity. The more the page is used, the higher the reference count. So we have valid, that is it currently there? Have you brought it in? We have reference, that is, did someone actually use it? Modified, did someone change the page or that part of memory in any way? And reference count, how many times has the process touched or used that part of memory? Now remember that it's possible to bring in memory, that's some part of memory, and the process does not use it, because maybe the software or the OS was anticipating you would use it a lot, brought in a lot of memory, and you didn't end up using most of it. That can happen. It's just like you go to the library and yes, there are many books that the library brings in, but you don't necessarily use every single book. So in the library scenario, consider this. That means I would say that a book is valid if we've brought it into the library. That means we've ordered it from wherever the publisher produces and brings it into the library. Reference means that someone has checked it out or has removed it from the shelf. That gives us an idea. Okay, yeah, this book is in use. Modified. Has someone tried to make some changes or comments? For books, it's not. We actually don't make changes in the books, hopefully. You're not touching the library books. But reference count would mean how often are people using a specific book. So that gives you an idea of how memory works. The same things we use in our daily lives, operating systems, all these are in. That's why I say if you have someone who's good at operating systems or computer systems, often they will be good at other things. Unfortunately, most of the world doesn't realize that a lot of the training that computer scientists go through, or people who take computer science courses go through, actually are very applicable to project management and, well, management in general. It's not just about code. These things are sound algorithms. And the nice thing about going through this with you, I hope, is you learn some techniques, not just for computer science, but for daily life. Right. Now, this is a diagram from the textbook from Silvershats to 36. I think it's 362 or 363. Anyway, it's figure 9.6, and it's showing the decisions that the system has to make. So it starts with reference 1. So I'm just going to go through this. I think it's a simple diagram. So it's saying when someone makes a reference to memory, we have to determine, do we have it in the page? So I here is whether it's valid or invalid. If it is invalid, if it's valid, we just send it back. So we are happy. Oh, we found it. It's valid. We send it back. And that's just like here. If I ask for page 0 and I say, oh, it's valid, that's awesome. We just say, oh, it's in memory. Go pick it up. But if we ask for it and it's invalid, that's I, it means we have to trap. That means we try to perform an operation, and a trap means that it's like an interrupt. You try to do something and it's illegal, and so some of the hardware would, or usually it has to be with hardware. If it's software, people will hack it. Some of the hardware will trigger or interrupt. The OS comes in, and the OS will go and figure out, based on all the algorithms, where the part of memory you're trying to access it. So it goes to hard disk, and there's this thing, and brings it in. So brings in the missing page into a free frame. So remember, physical memory they keep calling pages frames, and well, it's not they keep calling, that's the standard way. So frame would be a page in physical memory. So we bring it in physical memory, and then we update your page table, and finally we ask the process. So we bring back the process and say, try the instruction again. So it's possible that anytime a process runs an instruction, it may actually be asked to try it again. The same way, if you try and open a file, you go to the waiting queue. That if the file is not available, well, most of the time, even if you're trying to access the file is available, you may go to a waiting queue, and the operating system sets it up so that when you try and read, when your process tries to read, the data can come from the file or device, right? So this is the diagram. Everybody should be comfortable with this. It's not difficult, so we can use this. If I ask for a certain page, I have to check to see if it's valid. If it's valid, good for me, it's in memory. If it's not valid, in this case invalid, it means, so if I, for example, I wanted 2 or 3, or maybe I wanted internet browser page number 5, there's no physical page. It doesn't exist. There are only 4 of them. So it means I have to trap. That means go to the OS, and the operating system is going to go copy that page from the hard disk and bring it in. So I think this is one of the easiest chapters. Right, so the first one was hard, but this is very easy. Then we go to page replacement algorithms. Now, the reason why we have page replacement algorithms is because we know not everything will fit into memory. So what is the strategy we use for moving the pages between memory and virtual memory? Virtual memory is all the memory, both what you have in physical memory and the parts of the process that are in storage on disk. So the first one is optimal page replacement algorithm. Optimal means that anytime you ask me to do something, so if someone says, I have this computer that always does the optimal program start, or that's the optimal action, it means that the system can figure out what you need and can bring it in, so that by the time you say, I'm going to click on, oh, it's already running, I'm going to start typing, the system has already started typing for you. I mean, that would be an optimal system. So that is, in this case, bringing in pages. If it can always bring in the page that you will need before you need it, it's awesome, because you're running instructions, instruction 1, instruction 2, instruction 3, and we're saying that we can actually figure out the page that you are less likely to use and sort of bring in the one that you will be using next, so that we make sure we minimize I/O. I think that's probably a better definition. Optimal page replacement algorithm should minimize I/O. Now there's another algorithm, so least recently used. So this is, for example, very simple one that most people have. If you have your backpack, most students carry backpacks, and you put a whole bunch of books into your backpack. You get home every day, you come to campus, go home, come to campus. Before you set off from home, I'm sure if you open your backpack, you'd go through, and if there were any books you don't use or you least use, you are likely to leave those at home. That is the idea of least recently used. So whenever you're trying to say, oh, well, I have a new book and I'd like it to put into the backpack, you ask yourself, well, if there's no space, or I need to take out one of the books, which one am I going to take out? Least recently used says, well, take out the book that you have not used in a long time. Now, this sounds great, but as far as algorithms and thinking is concerned, just think about it as, well, if I just haven't been using it, maybe I should take it out. But of course, the flip side is, well, if you haven't been using it for a long time, maybe that's the day when it will be used. But least recently used just says focus on the one that has least recently been used. There's also the next algorithm, second chance algorithm. Right. So the second chance algorithm, so I'll go back to my diagram, would mean that I need to pay attention to my reference bit. Note that not all page tables will have all these bits, at least the valid bit, so it knows what is valid. But these are extras, so that help with the algorithms. So using a reference bit would say, whenever I have to take out a page, so I'll put the pages in like a round robin. We've done round robin scheduling, right? So it's the same idea. You have a round robin schedule for all the pages that a process is using. So if OS is running, set up these pages in round robin. If text editor is running, set up these pages in round robin. If internet browser is running, set these pages up in round robin. So what you do is, anytime, so that means it's always somebody's turn, and if I check and you find, I move to the next page. So the idea is, if I go to you and I check and you say, oh, you've been referenced. So for example, I start here and I say you've been referenced. That means I'm going to change this reference. I'm going to say, well, I just looked at your reference bit and it's been set, so I'll set it to no. So anytime I get to you, if you've been referenced, I set your reference bit to 0. Meaning that if I come back to you and I set it to no and I come back to you and it's still no, I kick you out. Right? And if your reference bit hasn't been set, it means that you were not in use, so I'll kick you out. But the idea of second chance is the first time I come to you, your reference bit is set. So it's yes, then I'll turn it to 0 or no, go to the next person. That means that if I need to replace somebody, I'll replace this guy. I go to the next, okay, there's nothing here. I go to this one, it's been set, I set it to no. This has been no, I kick it out. And I come back to the beginning of my round robin. If nobody has used this yet, this should still be no. And if that's still no, and that's your second chance, I kick you out. So that is the idea of second chance algorithm. So second chance algorithm again is like, I think people have heard of things like when a policeman stops you. So for example, let's say your policeman stops you and says traffic violation, your first offense. Right. Now, if I stop you again, I would say, well, you had a first offense and this is your second time, please go home. So they'll take maybe your license away from you or arrest you. So the idea is, if I see you and maybe I'll mark it that, okay, I just saw you, and that is the act of setting your reference bit to no. If it's yes, we set it to no. But if your reference bit is already no, it means you have no more chances. So the reference bit is used like a chance thing. So the moment I meet your reference bit is 1, I set it to 0. So I'm from yes to no. And then if I meet you again in the round robin and nobody has used you still, it's because whenever someone uses you, so that's whenever the process uses the page, it's going to set it to from reference it from no to yes. Then you have a second chance. So long as people keep referencing you, you are fine. Right, so that's the second chance algorithm. There's what we call the advanced second chance algorithm. And I'll go to this again. The advanced second chance algorithm uses 2 bits, not just a reference bit, uses a reference bit and a modified bit. So here are my options. It could be possible like this one. The page is there, but it says no. So it means nobody has referenced it and nobody has modified it. That is my first option to kick someone out. Because if it's not been modified and not been referenced, removing it is just like closing a file that has not been edited. So it was open, nobody was using it, I close it. Now in the second case, so 0, 1, so this is like 0, 0. So this is, if no means 0 and no means 0, that's 0, 0. The second one is 0, 1. That is, the page hasn't been referenced, but it has been modified. And that is a little bit more complex than just a no. No means I don't have to save it. But when it's no, yes, it means I have to save it. And then the next one is when it's yes, no, meaning someone has referenced it, but it hasn't been modified. So that's also nice. So that means on the grand scheme of things, if I've kicked out everything, the only ones left are yes, no's and yes, yeses, I'll be kicking out the yes, no's. Those who say yes, they've been referenced, but no, not modified. And of course, the one that is least likely to be kicked out are those that have been referenced and have been modified. So the idea is we are ranking the pages in terms of so the lowest priority, that's high chance to replace, are those that are no, not referenced or modified. Next we go to not referenced but modified, because it causes a little bit more work. Next we go to, oh, it's been referenced but not modified. And then finally the last one is it's been referenced and modified, and that is going to be dealing with the enhanced second chance algorithm. That means you use a reference bit and a modified bit. There are also 2 more, least frequently used and most frequently used. I like this discussion, and I hope that people who are taking computer science are realizing that a lot of decisions, algorithms, strategies, there are positives and negatives. SWOT analysis, I don't know, I think some people call it strengths, weakness, opportunities, and threats. So any type of system you're dealing with, people come up to me and say, what should I use, what should I use? And I would sometimes say, well, it depends on what your decision is, as far as you know what the advantages and disadvantages of your decision are. And sometimes as well, people come to me and say, oh, I have this perspective, someone has another perspective, I think I'm right. And I would say, well, there are different views of things. Sometimes there is only one way to do something. If so, do it. But sometimes there are 2, 3, 4, 5, many ways to do something. And this, I'm hoping this course is taking you through that, realizing that there are many ways to do something, so you should be comfortable with different approaches, different ways, so you pick the one that makes most sense. Right. So that's this one. So that means the last one, we use the reference count. That means that we go through, and if a page has been referenced, so anytime the process accesses the page, we increase the reference, but increase it. So when we're going to kick pages out, the ones with the least references, that means that that's the one the processes are not using. We're going to kick it out. So we can keep kicking out until we come to the ones with what? The highest reference. So the highest reference page, in this case like 10, that means the processor uses it 10 times. That means that is the highest priority. That means we are very unlikely to kick it out. And the least priority are the ones which are 0. So that is the least frequently used. Sorry, I didn't teach you the right words. Least frequently used. The other thing is there are two types: least frequently and most frequently, and both have their ideas. So least frequently is saying, well, I'm going to kick out those pages that I've not used or not been using frequently. If you kick those out, maybe that works, but depending on the algorithm or how the code is behaving, it's possible that if I've been using something for a while, like let's say let's say you have music, if you always play a certain track, someone may say, well, there's a good chance you play that track. That's true. But what if you are bored with that track and you're going to be picking the one you've not been playing at all? So that means there are actually two approaches to this. Kick out the one that you use a lot, or kick out the one that you've not used. Depending on the type of code you've written and how it's accessing the pages, then you may actually have a benefit from one or the other. Right. Now, when it comes to frames, right, we have to decide. So if I have physical memory, so let me just go back up to, this is my memory. We have to come up with a way to divide the pages or the frames here amongst all the processes. Right. So we can decide to have fixed, where we would say, okay, everybody should have 2 pages. And that means everybody has 2 pages. And that's, we can have a fixed allocation scheme. We can also have a proportional allocation scheme. So for example, we can say, since there are 3 of them, why not split this into, so there are 15 here, so why not give everyone 5, oh sorry, yeah, there are 15, so 16. If there are 16, then maybe I give 5, 5, 6. So I give the first process 5, the next process 5, the next process 6. Actually, we've almost got that breakdown, because this guy has 6, this guy has 5, so maybe this guy could get a little bit more. Okay, so that's the idea. So we have, as far as sharing, do we give everyone the same size, equal allocation, or do we make it proportional? Right? Because here's the thing, the more pages you give to someone in physical memory, the less chance they would fault. Faulting means that page fault means you try and access a page and realize it's not there, so the operating system has to come in, context switch, goes to storage, that's the hard disk, it brings it in. The more page faults you have, that means what? The more you may have been stalling, you wasted cycles. Right? So those are the issues, allocation of frames. Now, other issues, we talk about global and local allocation. And of course, that means that global and local replacement. So if a process wants a page that is currently not in main memory, are we going to replace one of the pages that belong to that process, or are we going to go and steal a page from or a frame from another process? So let me go back to this one. So for example, you take a look at this. Let's say the text editor was running, and let's assume that there was no more space, like all the white spaces have been used by somebody else, and the text editor was running, has these 2 pages, and says, I want a page. Should we try and replace like this one, the one that has not been used? Or should we go and steal from, so steal means we take another process, that's not the one that's currently running, kick out a page from some other process and give it to the one that's currently running. So that's stealing. Well, yeah, you can search the textbook, it's a term, stealing. So you can steal frames. So the idea is, For local, it means we always take pages from you, and for global, it means we can search outside and find other people to take pages from. There's also the idea of non-uniform memory access. I'm mentioning it because it keeps coming up a lot. In some systems, the hardware is set up such that different memory has different speeds. So when they are setting up, sometimes it's one of the things you have to consider. If I know that a certain type of memory or a certain range of memory is very fast, then maybe I'll deal with that side a little bit differently. If I know a certain range of memory is very slow, I deal with it a little bit differently. Now, please note that there are computer systems that have slightly different speeds, or sometimes if you buy even hardware. Now, sometimes when you're buying computers, they will try and make sure all the memory is of the same type, of the same rating, so you get the same performance across. And that would make the system a little bit better than to have some parts of memory where it's not working or a little bit slow or from a different brand, and another part which is very fast from a different brand. So those are real life issues. So when you say non-uniform memory access, that's what we're talking about. Now, thrashing. Thrashing occurs when a process is using space, and every time it tries to access it, it realizes that it keeps kicking pages out. So every time you try to get a new page, you have to kick somebody out. That actually means that thrashing is going on. So for example, let's say two people, A and B. So let me use this one, like this one. Let's say OS and text editor are running, and OS has been able to bring in all their pages, and text editor has brought in all their pages. There's no other space. And every time text editor is running, he says, I need one more page, and he goes to steal one page from the OS. And text editor runs fine for a bit, and OS comes in and says, I need a page, and he also steals from the text editor. So it means that every time we move from OS to text editor to OS, there is thrashing, meaning that he tries to take something and he doesn't get it, then he has to go pull it in and kicks out something that somebody else needs. Right? So thrashing can happen. This is getting long. I'm going to try and cut it short, but thrashing just means that you are anytime trying to access a page, also kicking out something else, and you don't get to use it often. You may not get to use it again, and immediately you try to use something else, you have to kick out another page. So that means thrashing is going on. So it's almost like you come to class with your backpack, and I say, oh, let's refer to silver shards. And you say, oh, I didn't bring silver shards. Let me go bring it. And you let's say you pick another textbook from your bag, Tannenbaum. And say, okay, let me take Tannenbaum back to your dorm and bring back silver shards. And then when you start reading silver shards, I say, well, the next book we are going to use is Tannenbaum. And you say, oh, great, I just took it back to the dorm. So you take out silver shards, you run to the dorm and bring back Tannenbaum. And again, I repeat, oh, we need Tannenbaum. And so you keep going back and forth. That's thrashing, or a very bad relationship bouncing between two people or two things. Thrashing. So that's a new term you can add. Right. Now, when we are trying to deal with or solve thrashing, there are two models. There are many. They can be hybrids, but I'm just presenting two. A locality model. So locality means that if we look at the address, there are other addresses that are close in the same range. Right. So that's locality. And working set means that there are certain addresses that, depending on what you're doing, you are using those addresses. So let me go back to this one. So for example, if an address is in 0 and another address is in 0, we would say, oh, they are in the same locality, meaning they are close page, they are in the same virtual page. And so 0 and 1, they are also close, so we can say, oh, those are all in the same locality. So that's the idea of the locality model. So it's better to say that 0, 1, and 2 are in the same locality compared to 0, 1, and 19. They are in different address locations, like this wide gap. Right? Now, when we talk about working set, now consider this. If a program is running, it may need different libraries. And I'm sure a lot of you have been running software. Maybe you're running a web server that uses a MySQL library. It uses an XML library. So depending on the web application that's running, certain libraries or sets of libraries are in use. And in that case, we would say there's a working set. There's a group of things you are working with. When it comes to memory, it's the same thing. Currently, if you take OS, maybe my working set, look at this carefully, this is 644. It means that whatever the OS is doing now, it's using 0 1912 a lot. So that could be considered my working set. Right. So that is the idea of the working set. It's that there are these pages that, depending on what you're doing, you're using them a lot. So that's a working set model. Now, yeah, proportional allocation. Allocation algorithms come back into thrashing. It doesn't have to be proportional, so I have to take that off. It doesn't have to be proportional, but the idea is, if we allocate you enough memory, you will not be going through the whole thrashing business. So if we deal with allocation properly, we may solve some of the thrashing issues. So in summary, this is one of the shorter chapters. We have virtual memory, and we can compare that to main memory. So virtual memory is memory from the perspective of the process. So from the perspective of the process that's running, or process is running, we look at how do we replace pages, virtual memory pages. Of course, it relates to main memory, but there are these allocation algorithms. And then we also talked about different issues with allocation and replacement. Now, thank you for watching. I hope you've enjoyed the class. There are a few other issues that during the review we'll talk about. That's practical things you can take in daily life. There are file systems, security. I think the other thing that's big that we really have to talk a little bit about it. It's been implied, but I just need to send you off on a good note. Is about fault tolerance, having backups, having redundancy. Because these days there is enough hardware to make it feasible. And because the cost of computers, so if you consider that maybe in a year you make a certain amount of money, maybe 100, and if you had bought that extra hard drive for just 10, it could have saved your job. I would say go for it. Yeah. So in computing, sometimes you do have to sit down and ask yourself, yes, there are all these things, but if you put certain software, certain hardware, certain practices in place, it may cost a fraction of your income, or a fraction of the percentage of the assets of the company, but I think it would actually save you a lot. So yes, there's all this thing we're doing about operating systems, but if we look at it the other way, we have to use this to advise ourselves to do the right thing and make sure that all the systems that are deployed to solve problems make our lives better, make things more efficient, work well. So thank you for watching the last one. I think I'll probably make some more, but this is the last one for virtual memory.